Hello students, today let us discuss the topic linear measurements using Vernier Caliper. So first of all, Vernier Caliper is a measuring instrument and it was invented in 1631 by a French mathematician, Pierre Vernier. Vernier caliper is a measuring instrument invented by French mathematician Pierre Vernier. So Vernier instruments are being used for more than 2 centuries. It was invented in the year 1631. Vernier caliper or Vernier scales provide a least count of at least 0.0 mm or less. So this will improve the measurement accuracy of an instrument. So it is mostly used in the engineering field. Vernier scale provides a least count of up to 0.01 mm or less, which increases the accuracy of the instrument. So, the basic principles of Vernier scale. So, what does a Vernier scale consist of? A Vernier scale consists of two scales. Okay, the main scale and the Vernier scale. Main scale and the Vernier scale. The main scale has graduations in millimeters up to minimum division of 1 mm. Main scale has graduations, that is markings are present on the main scale up to minimum division of 1 mm in millimeter. The Vernier scale also has graduations having 10 equal divisions. Vernier scale also has graduations having 10 equal divisions. So the scale readings on the main scale are called as main scale division. So in this example which I have taken here, the Vernier scale divisions, that is the VSD, equal to 9 main scale division, that is MSD. VSD, that is the Vernier scale division, 9 is equal to 9 main scale division, that is the MSD. So using this MSD and VSD, we have to calculate the least count. So we will go into further calculation of least count later. Now about the making or the construction of the Vernier caliper. So Vernier caliper, as I have told you, consists of two main parts. The main scale engraved on a solid L-shaped frame. Okay, so here this is the main scale or the fixed scale shown in this figure. So this is on a solid L-shaped frame. This is called as the main scale. And the Vernier scale that can slide along the main scale. So this is the Vernier scale here as shown in this figure, and it can slide along the Vernier scale. Because of the sliding nature of the Vernier, there is other name for this scale. It is also called as the sliding caliper. So a Vernier caliper consists of two main parts. It is the main scale and the Vernier scale. The main scale is engraved with graduations on a solid L-shaped frame. The Vernier scale slides along the main scale and has graduations on it. because of the sliding nature of this vernier scale, it is also called as a sliding caliper. It is also called as sliding caliper. If the graduations on the vernier scale are less than main scale division, such a vernier is called as the forward vernier. Values of one vernier division, scale division, is less than one main scale division, then such vernier is called forward vernier. For example, if 10 vernier scale divisions are equal to 11 main scale division, the value of one vernier scale division is more than that of one main scale division. Such vernier scale is called as the backward vernier. For example, if 10 VSDs are equal to 11 MSDs, that is the main scale divisions, then value of 1 VSD is more than 1 MSD, right? Then such vernier scale is called backward vernier. So this vernier scale is either made up of stainless steel or tool steel depending upon the nature of severity of application. So we have to see in what kind of application we are using this vernier scale, and then it is made up of either stainless steel or tool steel. Now, what are the main parts of the vernier caliper?
Now we will discuss the main parts of vernier caliper. So it has the L-shaped frame which also serves as the fixed jaw at its end. So this is the L-shaped frame. This is serving as a fixed jaw at its end. So L-shaped frame which acts as fixed jaw at its ends. Then there is a movable jaw which also has a vernier scale plate and can slide over the entire length of the main scale. So there is a movable jaw. So this jaw is a movable jaw and it has vernier scale on it. So we can see there is the vernier scale engraved on it on the, and it can slide over the length. So this jaw can move over the length of this vernier caliper or the main scale. So the second one is the movable jaw which has vernier scale on it or vernier plate. It can slide over the entire length of the main scale. There is a clamping screw which will enable clamping of the movable jaw in a particular position after the jaw has been set accurately over the jaw being measured. So there is a clamping screw. This screw will allow us or will make us to fix this movable jaw in a particular position. So after you have placed some workpiece here, you have to fix this movable jaw. So with the help of this clamping screw, you can fix the movable jaw at whatever position we require. Enables clamping of the movable jaw in a particular position. So this clamping screw will arrest or it will stop the further motion of the movable jaw, so that the operator or the person who is taking the readings may note down the readings in a convenient position. So in order to capture a dimension, what the operator has to do is he has to open out the two jaws, he has to hold the instrument over the jaw and slide the movable jaw inward until the jaws are in fixed or firm contact with the jaw. So here how the measurement is done, or what is the procedure the person who is using the vernier caliper has to follow to take down the readings. So first of all he has to open up these two jaws, okay, and then he has to place the workpiece or the component which he is measuring in between these two jaws, and he has to fix this, or he has to slide the movable jaw in whichever direction required, so that these two jaws are in firm contact with the component which we are measuring. So procedure to use vernier caliper. To capture a dimension, the operator has to open out the two jaws. First he will open the two jaws, then hold the instrument over the job or the workpiece which we are measuring. Then he will slide the movable jaw inward or outward, or whichever direction required. Then until the jaws, that is the movable jaw and the fixed jaw, are in firm contact with the jaw. So there is a firm adjustment screw which will enable the operator to accurately enclose the portion of the job where the measurement is required by applying optimum clamping pressure. So along with this clamping screw there is one more screw provided, that is the fine adjustment screw, and this screw will help the operator to accurately enclose the portion of the job where the measurement is required. So in the absence of this fine adjustment screw, the operator has to rely on his judgment to apply the minimum force that is required to close the two jobs firmly over the job. So if there is this fine adjustment screw, when you are tightening this movable jaw over the job, then what it will do is this screw will provide some clicking sound which will ensure that there is firm contact between these two jaws and the job which we are measuring. So in case of absence of this fine adjustment screw, which is not present in the diagram here, the operator has to rely on his judgment as to check whether there is firm contact between the fixed jaw and the movable jaw with the workpiece. So in the absence of this screw, so what happens if excessive force is applied? So if there is no fine adjustment screw, then to enclose the job between the two jaws, we may apply excessive force. So if you apply excessive force, then pressure increases, excessive application of pressure increases wear and tear of the instrument, and it may also cause damage to the delicate or fragile jobs. So excessive application of force will increase wear and tear of the instrument and may also cause damage to fragile jobs. So the two jaws are shaped in a manner such that they can be used to measure both the inside and the outside dimensions. So here we can see that the outside jaws, which are used to measure external diameter of an object. So these are the outside jaws. Now here there is a inside jaw which are used to measure internal diameter of an object. So to measure the internal diameter, so if this is the object, the red colored one is the object, then to measure its internal diameter, these two jaws can be used, and these jaws are used for measuring the outside diameter of this object. Now there is a tail which is used to measure the depth of an object. So there is a tail here in the vernier caliper end, there is a tail given, and this tail can be used to measure the depth of an object. So the two jaws are shaped in such a way that they can measure both inside and outside dimensions. So the nibs which are provided on the top of the scale or the on the head of the scale can be used to measure the internal diameter. Outside jaws are used to measure external diameter of objects. The tail present at the end of the scale can be used to measure the depth of an object. So all these things are shown in this figure. So measuring the diameter is easier than measuring between the flat surfaces, because the diameter is the greatest distance separating the reference and the measured points. So compared to the measurement between the flat surfaces, the area of contact between the caliper and the job is much less in the diameter measurement. So measuring of diameter is easier using this vernier caliper, as the area of contact is less in diameter measurement between the jaws and the job than in flat surfaces. So the next topic which we have to know about is the guidelines for using vernier calipers. So what are the guidelines which we have to follow for proper use of a vernier caliper? So the first one is clean the vernier caliper and the job being measured thoroughly. We have to clean the vernier caliper, that is the vernier scale, properly, along with the component or the job which we are measuring using this vernier caliper. So we have to ensure that there are no burrs attached to the job which may have resulted from previous machining process. So the job which we are measuring here must be cleaned thoroughly, and we have to ensure that there are no burrs or no surface impurities present on the job by previous machining process. So first one is clean the vernier caliper and the job being measured thoroughly. The next point is when the caliper jaws are fully closed, it should indicate 0. If it does not, then we have to calibrate it or we have to repair it. So we have already seen the caliper has two jaws, one is the fixed and one is the movable. When these two jaws are close to each other or they are fully closed, then if this is the fixed jaw, this is the movable jaw, when they are in close contact with each other or they are fully closed, then the scale readings must be 0. If not, then we have to either calibrate the vernier caliper or we have to repair it. So when the caliper's jaws are fully closed, it should indicate 0. If not, the caliper must be recalibrated or repaired. The third guideline says that we have to loosen the clamping screw and slide the movable jaw until the opening between the jaws is slightly more than the component to be measured. So we have to loosen the clamping screw and then we have to move the or slide the movable jaw to a distance slightly larger than the component placed in between these two jaws. So loosen the clamping screw and slide the movable jaw The fourth guideline is place the fixed jaw in contact with the reference point of the feature being measured and align the beam of the caliper approximately with the line of measurement. Now place the fixed jaw in contact with the reference point of the feature being measured and align the beam of caliper with the line of measurement. The fifth guideline says that slide the movable jaw closer to the feature and then operate the fine adjustment screw to establish light contact between the jaws and the job. So now sliding the movable jaw closer to the feature or the component being measured and operate the fine adjustment screw to establish light contact. So if you apply more pressure, then it will damage both the job as well as the jaws. That is why there must be light contact between the jaws and the job. The next guideline, that is the sixth guideline, is tighten the clamping screw on the movable jaw without disturbing the contact between the caliper and the job. Now we will tighten the clamping screw on the movable jaw so that the movable jaw will not be able to slide. We will fix it at a single place. The seventh guideline says that remove the caliper and note down the readings in a comfortable position, holding the graduations on the scale perpendicular to the line of sight. Now we will remove, after tightening the movable jaw and making contact with the job, we will remove the caliper and note down the readings in a comfortable position, holding the graduations on the scale perpendicular to the line of sight. That is, it must be clearly visible. The eighth guideline says that repeat the measurements a couple of times to ensure accurate measurement. So after noting down the readings, we will again repeat the measurement so that we will get accurate readings. The next guideline is, after completing the readings, loosen the clamping screw, open out the jaws and clean and lubricate them. So after taking down the readings, we will loosen the clamping screw, open out the jaws and clean and lubricate them. The 10th guideline says that we have to store the caliper in the instrument box provided by the supplier. So we have to avoid keeping the vernier caliper open for long durations, since it may get damaged by other objects or by contaminations. So always store the caliper in the box provided by the supplier to avoid damage or contamination. The last guideline is that we have to strictly adhere to periodic calibration of vernier caliper. So it must be periodically or time to time calibrated. So strictly adhere to periodic calibration of vernier caliper. So these are the guidelines for using the vernier caliper. Now we will see how the least count of this vernier caliper is calculated. So calculation of the least count. So the minimum length or thickness that can be measured with the vernier caliper is called as the least count. So first of all, what is least count? So it is the minimum length or thickness which can be measured with a vernier scale. So if vernier scale division is given as VSD, main scale division is given as MSD, N is the number of divisions. So for forward vernier, N vernier scale divisions is equals to N minus 1 main scale division. So VSD is equals to N minus 1, that is vernier scale division is equal to N minus 1 divided by N into main scale divisions. So least count is equal to 1 main scale division minus 1 vernier scale division, and this can be written as is equal to 1 minus N minus 1 divided by N into main scale division. So from this we can write least count is equal to 1 main scale division divided by N. So the total readings is given as MSR plus VC into LC, where MSR is the main scale reading. MSR is main scale reading. LC is the least count. VC is the vernier coinciding division. So this is how we calculate the least count and the total readings for the vernier scale.
The next topic is types of vernier caliper. So as we can see in the figure, there are three types of vernier caliper. The first is the digital vernier, the standard vernier which we have already discussed, and the dial vernier. So the first one, let us consider dial caliper. So why this is a modification of this standard vernier caliper? What is the modification made? Here the readings are taken with the help of a dial which is present on the caliper. So in the standard vernier caliper, what happens? We will have to take down the readings Okay, we have to see the main scale division and the Vernier coinciding division. Okay, then we have to manually calculate the least count, and then only we will be able to find the dimensions of the measured quantity. Okay, so this is a very large process, but here in dial caliper what happens, there will be least count present in the dial itself, so which will be indicated on the face of the dial. So this is the dial caliper, and there is a dial gauge present on the vernier scale. The working is same as that of the vernier caliper, as the standard vernier caliper, only that the least count will be shown on the dial face. But this dial caliper is more expensive than the vernier caliper, so it may be subjected to malfunctioning due to delicate nature of the dial mechanism. So here it is a small of the standard vernier to avoid the process of manual calculation on the scale, which will give the least count measure. This is more than standard vernier and may be subjected to malfunctioning due to delicate nature of dial. So we already know about the standard vernier caliper. Now the next modification of the standard vernier is the electronic or digital caliper. So it is an electronic digital caliper is a battery operated instrument that displays the readings on the LCD screen. So this display will eliminate the need for calculation and provides an easy way for taking the readings. So LCD display is provided with a on and off button. The great advantage of this electronic digital caliper is the electronic calculator functions and capability to be interfaced with a computer. So this instrument is battery operated. Liquid crystal display, that is the LCD. So it eliminates the need for calculation and makes it easy to take readings. The display is provided with on and off button. It can be interfaced with computer and has a built-in calculator. So this is all about the dial caliper and the electronic or digital caliper. The next one is the depth gauge. So we have already seen how the vernier caliper can be used to take the readings even for the depth also, but it cannot take readings or measurements finer than 1 mm. So a vernier depth gauge is an instrument which can be used to measure up to 0.01 mm or even finer accuracies. So this depth gauge was developed because used to measure up to 0.01 mm or even finer accuracies which cannot be measured with the standard vernier. It can measure only up to 1 mm depth. So here we can see that this instrument consists of different parts. So here we are keeping the workpiece here and the depth being measured. So this is the base of the depth gauge. There is a movable head, there are locking screws, then there is vernier scale, and there is a main scale on which the vernier scale is moving. Then we have fine adjustment screw here. So here, just like the Vernier Caliper, even this works on the same principle. So the lower surface of the base has to butt firmly against the upper part or the hole whose depth has to be measured. So here the workpiece has to be kept in such a way that the base has to butt firmly against it. Okay, so it has to sit against this workpiece whose depth has to be measured. The vernier scale is stationary and screwed on the slide, whereas the main scale can slide up and down. So here the vernier scale is fixed, it does not move, and this main scale can slide up and down. So we should not exert the force on the workpiece. So there is a fine adjustment screw so as to place the workpiece without exerting more force. Then what is done? After the workpiece is correctly butted to the base of the depth gauge, with the help of locking screws, we lock it in position and then we will take the readings. And then after the readings are taken, as per the guidelines used for measuring from the vernier caliper, the same guidelines need to be followed even for the vernier depth gauge. They have to be cleaned, they have to be periodically calibrated. Okay, all the mandatory functions have to be carried out for proper working of them. So the first point is the vernier scale is stationary and screwed on both the sides. The main scale can slide up and down. So the locking screw has to be slided. The nut on the slide has to be loosened to move the main scale. The main scale is slided up and down by loosening the nut or the locking screw. Then the main scale is lowered into the hole which has to be measured. Then with the help of locking screw, the scales and the workpiece are maintained to have delicate contact with the surface of the job or the workpiece with each other. Then the readings can be noted down, after which periodic cleaning and lubrication is mandatory. The next topic is vernier height gauge. So here, as we can see that the construction of the vernier height gauge is similar to that of depth gauge, but here the measuring jaw and the base are mandatory here. There is a vernier scale here as well, main scale, then there is a fine adjustment clamp slider. Here, unlike depth gauge, the main scale does not move here. Here the vernier scale is mounted on the slider, which is sliding up and down. This is the fine adjustment screw. So the object to be measured has to be placed. The height of the object which has to be measured is placed between this measuring jaw and the base. And then clamping is done with this adjustment clamp, and for delicate fixation of the job that is measured and the measuring jaw, this fine adjustment screw is given so as to avoid wear and tear of the material as well as the job that is being measured. So with the help of this adjustment, we will place the object here and we will measure the height of the job. So in a vernier height gauge, the graduation scale or the bar is held in vertical position by a lapped base. In this instrument, the graduation scale is held in vertical position by a lap. The feature or the job being measured is held between base and the measuring jaw. The measuring jaw is mounted on a slider which goes up and down. The vernier scale mounted on the slider and gives accuracy of 0.01 mm, that is millimeter. So these gauges are available in sizes ranging from 150 to 500 mm for precision tool room applications. So they are available in sizes ranging from 150 to 500 mm. The fine adjustment screw ensures delicate contact between the measuring jaw and the job to be measured to avoid wear and tear of both the height gauge and the job which is being. So this is about the vernier height gauge.